Yeah, that clock keeps ticking till we start up in here. Yeah, that clock keeps ticking till we start up in here. If you came to learn chemistry, you did your part. Time is ticking down, so just be ready, cause it's about to start. When we solving for problems, we solve it information. You know Ben's Chem videos will provide you with equations. Never have to stop and think about it, this the station that will provide you with the chemistry all in relation. If you came to learn chemistry, you did your part.
Hello everyone, and welcome to the second episode of the Organic Chemistream, a live stream in which we talk about organic chemistry. Let me tell you guys something. I am really excited. I don't know why exactly I'm so excited, but I am more excited for this stream coming up tonight than I have been for an upcoming stream in a very long time. So thank you for being with us tonight. So what are we going to talk about? Well, we are going to talk about the general chemistry stuff that is really important for having a good rock solid foundation for taking a crack at understanding organic chemistry. So really, at the root of it all is chemical bonding, right? Organic chemistry, as we defined last week, is the study of compounds that contain carbon, right? And carbon likes to form all kinds of bonds to other carbon atoms, bonds to non-carbon atoms, long chains of atoms, rings of atoms, all kinds of stuff, right? So really, at the core of organic chemistry is chemical bonding. That's what we're going to talk about tonight. So I think a good place to start when talking about chemical bonding is to go over Lewis dot structures, right? So Lewis dot structures, what do they tell us? They tell us in a molecule which atoms are connected to which. They tell us what's going on with the valence electrons. They tell us what kind of covalent bonds there are between atoms. In other words, are they single or double or triple covalent bonds and all that good stuff. So we can get a lot of useful information from Lewis dot structures. But of course, in order to draw Lewis dot structures for molecules, it's important to be able to draw Lewis dot structures for individual atoms. So just a reminder, you probably already know this, but just to make sure everybody's up to speed. When you draw a Lewis dot structure for an atom, what does it represent? Well, the chemical symbol in the Lewis dot structure for an atom represents the nucleus and core electrons. So the nucleus and all of the inner non-valence electrons. And the valence electrons, which of course are the electrons in the outermost principal energy level, the outermost shell of the atom, they are represented by dots. And so, for instance, we can look at nitrogen. If we wanted to draw a Lewis dot structure for nitrogen, we would draw the chemical symbol for nitrogen, a capital N, with 5 dots around it. And we would draw those dots basically imagining as though there are 4 sides around that chemical symbol, north, south, east, west. You can think of it like that. And you would place 1 dot on each side. And if there are 5 or more valence electrons, you would start to sort of double up after one side, after all 4 sides each have 1 dot, right? And so if you were to do that for nitrogen, this is what your resulting Lewis dot structure would look like. And the electron configuration for nitrogen is also shown down here. It's 1s2, 2s2, 2p3. So if you're fuzzy on how to draw or write the ground state electron configuration for an element, I do have a video on that if you are interested. So that's how you draw a Lewis dot structure for an atom. And so that kind of raises the question, well, how do you know how many valence electrons an element has? And in the case of main group elements, right, the elements that are shown in this periodic table here, the S and P blocks of the periodic table, it's pretty easy to find the number of valence electrons. It's simply equal to the group number, right? So if it's in group 1, it's got 1 valence electron. If it's in group 5, like nitrogen, it's got 5 valence electrons, and so on and so forth. The only exception is helium, which has 2 valence electrons, even though it is in the 8th group of the main group elements, right? So when we look at the elements in the periodic table and we look at how many valence electrons each one of them has, we can also get an understanding of the predictable bonding behavior of these main group elements, right? So this slide here shows a few commonly encountered elements within organic chemistry: carbon, nitrogen, oxygen, hydrogen, and the halogens, fluorine, chlorine, bromine, and iodine, right? And their corresponding Lewis structures are shown in this middle column here. But then the other column, it says the number of bonds that are on an uncharged atom, right? So the idea here is that each of these elements forms a predictable number of bonds. Carbon generally forms 4 bonds. Nitrogen generally forms 3. Oxygen, 2. Hydrogen, 1. Halogens, 1. Right? And so what's going on? Why do these elements behave so predictably and form a predictable number of bonds? And the number of bonds, I'll just answer that for you now. The number of bonds that are formed depends on the number of unpaired electrons that you find in the Lewis dot structure. So carbon, for instance, 4 unpaired electrons, so it forms 4 bonds. Oxygen over here, it's got 2 unpaired electrons here, 2 unpaired valence electrons, and so it forms 2 bonds. And so you might be asking yourself, well, why do these bonds form in the first place, right? And you probably already know this, but like I said before, it's worth reviewing once again, is something called a noble gas electron configuration, right? So noble gases, the first 2 of them are shown on the screen here. We've got helium with atomic number 2 and neon with atomic number 10, right? And the orbital diagrams of these 2 noble gases are shown here. So in both of these cases, the outermost principal energy level, the valence shell, is completely full of electrons. And there is a special stability. The electrons that populate the orbitals in a full valence shell enjoy a special low potential energy sort of environment, right? And so, for instance, helium, right? Helium is in the first period of the periodic table. In the first period, you have the n equals 1 quantum number principal energy level, of which there's only the s sublevel, in which there is only 1 orbital that can contain 2 electrons, right? So the 1s sublevel, it's completely full of electrons, so the outermost principal energy level is full of electrons. And in the case of helium, we call this a duet, right? Duet means 2. And in the case of neon, right, there are 4 orbitals. There's a 2s and 3 2p orbitals that are in the valence shell of neon, right? And so that equates to 8 electrons, right? Because you got 4 orbitals. Each orbital can hold 2 electrons. And so in the case of neon, we have what we call an octet, right? And again, octet just means a full outermost principal energy level of electrons, which is a very, very stable, very happy, very low potential energy situation, right? And so other nonmetals like carbon, like nitrogen, like oxygen, like hydrogen, what they will do is they will form covalent bonds with other atoms in an attempt to form like this mutually beneficial arrangement, right? So imagine a carbon atom comes up to a hydrogen atom and says, hey man, what if I share one of my unpaired electrons with you? You can share your unpaired electron with me, and we'll kind of scratch each other's back, right? We'll fill each other's valence shells. We'll lower our potential energy, and we'll both be better off for it, right? So you can think of these other elements as like jealous of the noble gases. They want to form bonds in a way that fills up their valence shells completely so that they can enjoy the same electron configuration that the noble gases have, right? And so if we consider, for instance, methane. Methane is a compound with the formula CH4, right? And the orbital diagrams of carbon and hydrogen, individual carbon and hydrogen atoms, are shown on your screen here, right? So if you look at carbon, right, how many electrons does carbon need to have a full valence shell? In other words, to have the same electron configuration as the nearest noble gas, which happens to be neon. Well, that would be 4, right? In other words, carbon is 4 electrons short of an octet. That sounds like something you would use to insult somebody, like, oh yeah, you don't want to listen to him. He's like a few electrons short of an octet. I don't know. I thought that was funny, but anyway. So carbon needs 4 electrons to get an octet, and then you have hydrogen, right? Hydrogen needs just 1 electron to achieve a duet, which is the noble gas electron configuration that would be ideal for a hydrogen atom, right? And so what happens is the carbon will form these single covalent bonds, right? The carbon will form a single covalent bond with 4 hydrogen atoms, right? And that allows the carbon to get an octet, to get 8 electrons around it, to get a noble gas electron configuration. And that also allows the hydrogen to achieve a duet, another noble gas electron configuration, right? So it's like I said, it's a mutually beneficial arrangement. This is sort of the driving force that governs the behavior of these nonmetals that causes them to bond like this, right? And so another thing we can consider, which I think is time well spent, is to consider the diatomic elements. Remember, diatomic means that that element is composed of molecules, each molecule containing two atoms of the element covalently bonded together, right? And hydrogen, oxygen, nitrogen, and the halogens, fluorine, chlorine, bromine, iodine, they all exhibit this behavior where they exist as these diatomic molecules, right? And they exist as diatomic molecules for the same reason why carbon and hydrogen bond together to form methane, right? It's because those atoms can benefit one another by forming those covalent bonds and filling each other's valence shells. Notice in the case of H2, each of these hydrogen atoms, whoops, jumped a slide by accident. Each of these hydrogen atoms has a duet. So it's happy, it's satisfied, it's got a low potential energy, right? Oxygen, if you hide each oxygen atom and you count the total number of valence electrons around each of them, you'll find that each oxygen has 8 valence electrons, an octet, a noble gas electron configuration as well. Notice also that the oxygen forms a double covalent bond, which is 2 pairs of electrons shared between the atoms, right? Nitrogen, same thing. If you cover up one of those nitrogens, you'll find that each one has a total of 8 valence electrons around it. Each one of them has that happy, stable, low potential energy octet that they all covet so much. And notice also that the nitrogen actually forms a triple covalent bond with the other nitrogen, 3 pairs of electrons shared between the two atoms. And then if you look at halogens, and again, this X is just sort of a substitute for fluorine, chlorine, bromine, and iodine. They all behave quite similarly, right? That forms a single covalent bond, and both of the atoms that are bonded together have an octet, right? So this is kind of the driving force. This is the behavior that governs the bonding behavior that we're going to study in thorough detail later on as we continue to study organic chemistry, right? And so now is the point in the video where I just want to briefly review how to draw a Lewis dot structure when you are given a chemical formula, right? So let's say you're given a chemical formula for a molecule or a polyatomic ion. You want to be able to draw the Lewis structure, which again ultimately tells you the connectivity, what atoms are bonded to what, and sort of where all the valence electrons are. Could you do that? What steps would you follow to do that? And these are the steps right here, so I'll just kind of launch into them briefly. Step 1 is to count the total number of valence electrons, and you add an electron for each minus, and you remove an electron for each plus. So if you're dealing with a polyatomic ion, you would either remove or add electrons according to what the charge of that polyatomic ion is. The second step is to draw the correct arrangement of the atoms, and there's a few things to keep in mind when you're doing this step. One is that the least electronegative atoms will be the central atoms. They will appear in the center. So if you have a choice between two atoms, you don't know which one to put in the center, the least electronegative element is going to go in the center. And we'll talk more about electronegativity later as well. Another thing to keep in mind is that hydrogen, since it only exists in the first principal energy level in which there's only 2 electrons, hydrogen can only form 1 bond. So hydrogen cannot be a central atom, because in order to be a central atom, you have to bond to at least 2 other atoms. So that's something to keep in mind. And then the third thing to keep in mind when you're looking for the correct arrangement of the atoms is that sometimes there's more than one possible arrangement. Happens all the time, especially with larger molecules, right? So that's step 2. Step 3 is to place a single covalent bond between all neighboring atoms. A single covalent bond, remember, has 2 electrons in it. The step 4 is to place lone pairs. So lone pairs, those are the electrons that belong to individual atoms that do not participate in chemical bonding. Place lone pairs on atoms, starting with terminal atoms, then moving inward, giving an octet to as many atoms as possible until all valence electrons are accounted for, right? So you put lone pairs on the atoms. And then finally, the 5th step is to, if necessary, move lone pairs between atoms to make double or triple covalent bonds as necessary to give all of the atoms in that entire Lewis dot structure an octet, of course, duet in the case of hydrogen atoms. So we are going to launch into an example where we do this. I'm going to do it somewhat quickly because, again, this is kind of a review. This is stuff we should be able to do already, but I'm doing this anyway just to make sure we're all up to speed. So this is what we're going to do. So we're going to be given a chemical formula of the nitrite ion, NO2 minus. So what we want to draw the Lewis dot structure for the nitrite ion, NO2 minus. So in order to do that, I'm going to take you guys to the whiteboard, and I invite you to follow along as we go through this. So again, I'll write that chemical formula over here. It's the nitrite ion, that's NO2 minus, right? So the first step is to count the total number of valence electrons, right? So starting with the nitrogen, right? Nitrogen has how many valence electrons? That would be 5, and we know that because it's in the 5th group of the main group elements in the periodic table, right? And then we have oxygen. How many valence electrons does oxygen have? Oxygen has 6, and according to the chemical formula, there are 2 of them, 2 oxygens, for a total of 12 coming from that oxygen. And then also, since we have a minus here, that adds 1 electron, right? So we have 5 plus 12 plus 1 for a total of 18 valence electrons. Okay, so that's step 1, count the total number of valence electrons. Step 2 is to draw the correct arrangement of the atom, right? So there's 2 possibilities. We could either have a nitrogen in the center with 2 oxygens around it, or we could have an oxygen in the center with an oxygen and a nitrogen around it, right? So one of these is correct, the other one is incorrect, and I would invite you to think about this one for a second and ask yourself which one of these is correct and why. Okay, so hopefully you've given it some thought. It turns out that this one, in which oxygen is in the center, is incorrect. The reason why it's incorrect, again, is because the least electronegative atom is the one that is going to be the central atom. Between nitrogen and oxygen, oxygen is more electronegative than nitrogen, so we put nitrogen in the center. So I'm going to go ahead and just erase this incorrect one right here. So we have the correct arrangement of the atoms, right? It's a nitrogen with an oxygen on either side. Then what we're going to do, the next step, is to place a single covalent bond between all neighboring atoms. So we're going to place a single covalent bond there. Remember, single covalent bond is 2 electrons, right? So we just placed 2 single covalent bonds. So we've accounted for 4 of our 18 valence electrons. So we're going to take 4 away from 18, and that's going to give us 14 valence electrons left to play with here. Elgato 2 says, do you have a 3D model of a bond? Yeah, I actually do have a couple of 3D models that I'm going to display later on in this presentation. So stick around, because we're definitely going to be playing with some molecules here. All right, so back to this Lewis structure for a second. So we have 14 valence electrons. We have just completed the step in which we fill a single covalent bond between all neighboring atoms. The next thing that we need to do is we need to place lone pairs on the atoms, starting with the terminal atoms, the oxygens, and then moving inward until all valence electrons are accounted for, right? So we have 14. So there's 2, 4, 6, 8, 10, 12, right? The oxygens have an octet. I have 2 valence electrons left, so there's nowhere else to put them except for this nitrogen atom, right? And that takes care of all of our valence electrons, right? So we don't have any more valence electrons to place on any of these atoms here, right? And then the final step is to, well, we're going to check to make sure all 3 atoms have an octet, right? If we cover up the nitrogen and the oxygen over here, it looks like this oxygen on the left has an octet. Looks like this oxygen over here on the right also has an octet. But look at the nitrogen. The nitrogen doesn't seem to have an octet. The nitrogen has 1, 2, 3, 4, 5, 6 valence electrons around it, not 8. So how do we fix that? Well, we move lone pairs into the bonding region between the atoms to form double, or in some cases, triple bonds, right? So what I'm going to do is I'm going to take one of these lone pairs on this oxygen here, and I'm going to move it between the oxygen and the neighboring nitrogen atom, to form a double bond. And it looks like now that we formed that double bond, the nitrogen is just as happy with its octet as the two oxygen atoms. So this would be the correct Lewis dot structure here for the nitrite ion. And so hopefully you've seen this step-by-step technique before. I hope this is something that is kind of coming back to you. Again, that's the whole point of this stream, is to kind of, bring our memory up to speed, just refresh our memory on all this stuff, because it's really, really important. All right, so we're going to go back to the PowerPoint real quick, and we're going to move on. All right, so let's talk about something called Kekulé structures. So Kekulé structure, very, very similar to a Lewis dot structure. The only difference is that instead of using a pair of dots to represent a single covalent bond, we use a line to represent a single covalent bond, right? And so the nitrite ion, the thing that we just drew, both the Lewis and the Kekulé structures of the nitrite ion are shown here. Personally, I'm a big fan of the Kekulé structure because it just looks cleaner and sexier to me. Not so many dots all over the place. So my personal preference is for Kekulé structures over Lewis structures all day, hands down. So you'll often see the terms Lewis and Kekulé structures sort of used interchangeably, but kind of doesn't really matter as long as we agree that we know what we're talking about here. We know what a bonding pair is, what a lone pair is, what a single, double, and triple covalent bond is. As long as we all understand that, then it's kind of up to whoever is doing the drawing what convention they want to use for their notation, right? So let's go ahead and move on. So one thing that's really, really important to point out is the deficiency of Lewis Kekulé structures, where they fall short, right? So if we turn our attention back to methane, CH4, this is a Kekulé structure of a methane molecule, right? And if you look at this, it sort of tends to imply that all five of these atoms here, the carbon and all four hydrogens, are all in the same plane, and that the angle between those neighboring bonds is a right angle, is 90 degrees. In other words, let me enlarge myself a little bit, because I got to show you a molecular model here, right? So if we were to look at this Kekulé structure of methane and interpret literally as though the structure is intended to show geometry, we would expect the molecule to look something like this, right? Where all five of those atoms are in the same plane. It's sort of shaped like a square, in which you got your carbon atom in the middle there, right? And your hydrogen atoms pointing to the four corners of a square. But this is not the case, right? Methane is not actually shaped like that. Instead, methane is shaped like this. This is what we call a tetrahedral molecule, a tetrahedral geometry. We'll talk more about that shape a little later. But it's very, very important that we understand that Lewis Kekulé structures in general are not meant to show geometry. They are only meant to show connectivity. They are only meant to show what is bonded to what, and of course what's going on with all the valence electrons. Now, let me take you to the whiteboard for a second here. Kind of going off the cuff. I didn't plan this, but I want to take you to the whiteboard for a second, and I want to show you guys one way that the deficiency of Lewis Kekulé structures can kind of be mitigated a little bit, right? So we were looking at that structure of methane earlier, right? That CH4, right? So we know that it's not shaped like a square where all five atoms are in the same plane. It's actually shaped something called tetrahedral, right? And so if we wanted to draw that a little bit more three-dimensionally accurately, we could draw it. I'm not really doing a good job drawing straight bonds here, but we could draw something that looks kind of like this, right? So, and then each of these is a hydrogen atom, right? Right? So notice that we have three atoms that are sort of in the plane of the screen here, and then we have one atom whose bond is represented by a heavy wedged line, and another bond to a hydrogen atom that is represented by a light dashed line. So the way that that's sort of intended to represent things is the heavy wedged line represents a bond that is projecting outward. It is projecting like towards you, away from the screen, right? On the flip side, the dashed line is something that projects like into the screen, like away from you, going backward. I hope you can sort of see that here. So this is one way that Kekulé structures, Lewis structures, can sort of be modified to be more three-dimensionally accurately. So I just wanted to point that out as we go back to the PowerPoint here. So again, we know what Lewis structures do and what they don't do, what they are supposed to represent and what they're not supposed to represent. It's very, very important that we understand that. So in order to understand better the shapes of molecules and what governs the shapes of molecules, it's important to know about a little bit about valence bond theory, right? So valence bond theory basically describes a covalent bond as an overlap of orbitals. And there are two possible overlaps, and those are called sigma and pi bonds. Sigma bonds and pi bonds. Very, very important that we understand what a sigma bond is, what a pi bond is, and the difference between the two. So starting with sigma bonds, what a sigma bond is a linear head-on, head-to-head overlap of orbitals, right? And anytime you see a single covalent bond in a Lewis Kekulé structure, not a double bond, not a triple bond, but anytime you see a single bond, that single bond is always going to be a sigma bond. It's always going to be a head-on overlap. So shown on your screen here are two examples of sigma bonds here. So the first one up here is for a diatomic hydrogen molecule. So you have like two individual hydrogen atoms with their valence electron in the 1s orbital, right? And then they come together to form a sigma bond, a head-on overlap of those two 1s orbitals. And we would denote that using the Greek letter sigma and then a subscript 1s to 1s, right? So it's a sigma bond between two 1s orbitals, right? If we look at diatomic fluorine, for instance, right? Fluorine, individual fluorine atoms, they have unpaired valence electrons that are located in 2p orbitals, right? And so when a single covalent bond forms between two fluorine atoms, it's a sigma bond. It's a direct overlap of those 2p orbitals. And this would be a fairly decent way to represent that. And of course, we would denote that with a sigma and then that subscript that says 2p to 2p, right? This next slide here is an example of what we call a heteronuclear sigma bond, which basically is just a fancy word for saying a sigma bond between two different atoms, right? We have a molecule of hydrogen chloride, HCl, right? We've got a hydrogen atom whose unpaired valence electron is in a 1s orbital. You've got chlorine whose 1s electron is in a 3p orbital, right? And so when they form a covalent bond, those orbitals overlap, giving us a sigma bond between the 1s of the hydrogen and the 3p of the chlorine. So just want to check in with you guys who are watching so far. Everything's sounding good. Everything not confusing, or if it is confusing, let me know. Just wanted to take the time to ask you guys for your feedback because we are going to move on fairly quickly because we got a lot of stuff to cover. It might be a long stream. I don't know. So, all right, I don't see anything yet. There's a little delay here, so perhaps I should wait a little bit longer. I don't know. By the way, if you are interested in supporting the stream, there's many ways to do it. You can leave a thumbs up. That helps with discoverability. You can donate via Streamlabs. Your donation actually appears live on the screen. If you're interested in that, there's a link in the description. And also, you could send a super chat or a super sticker if you're interested in those as well. Your support is much appreciated. Thank you very much. All right, so there's sigma bonds, direct linear head-on overlap. Now let's talk about pi bonds. So pi bonds are a sideways overlap. So instead of overlapping head-on, the orbitals overlap sideways, right? And this is not possible for s orbitals because s orbitals are completely spherically symmetrical, right? P orbitals have that dumbbell shape to them. So it's possible for p orbitals to have two possible orientations where they can overlap directly head-on or they can overlap sideways. So that sideways overlap, that's what we call the pi bond, right? So if you think about a diatomic oxygen molecule, right? As we saw a moment ago, diatomic oxygen is connected by a double covalent bond, and one of those two covalent bonds is a pi bond, is a sideways overlap of the 2p orbitals of oxygen. And so we would denote that with the symbol pi and the subscript 2p to 2p, right? This is a pi bond between 2p orbitals, right? So again, if we revisit the Kekulé structure for oxygen, we can see that these two oxygen atoms are joined together by a double covalent bond, but there's really nothing about the Kekulé structure that tells you what exactly is going on with the overlap of the orbitals that gives you this double covalent bond. It turns out these bonds are not identical at all, right? One of the bonds in that double covalent bond is a sigma bond, which is shown here in blue. It's the direct overlap of those 2p orbitals of oxygen. The other bond in the double bond is a pi bond. It's a sideways overlap of 2p orbitals, right? And so it's very difficult to draw these things in a way that I can label them and everything. I didn't actually draw these p orbitals that are shown in red as overlapping. I mean, that's how they really are. They really overlap. I couldn't really draw them that way because it would just be like a really big jumbled mess. And yeah, so I just kind of drew these like arcs to just sort of represent that, you know, these are the orbitals that are kind of interacting, that are overlapping, that are part of that double bond, right? So we now know that anytime you see a double bond in a Lewis-Kekulé structure, that double bond is composed of one sigma bond and one pi bond, right? If we look at pi bonding even further, another way, a good way to do that is to revisit the Kekulé structure for diatomic nitrogen, right? Looking at the Kekulé structure, we understand that diatomic nitrogen is connected together by a triple covalent bond. But what is the nature of that triple covalent bond, right? Of those three bonds, how many of them are sigma bonds? How many of them are pi bonds? And the answer is that one of those three bonds is a sigma bond, a direct head-on overlap. The other two bonds are pi bonds, right? And so I've given it my best attempt to try to draw this in a way that makes sense. I hope this isn't just one big convoluted mess to you, but allow me to explain, right? So shown in blue here is the sigma bond. That's the direct head-on overlap, right? And then shown in red, sort of pointing up and down, are one pi bond, right? So that whole red thing, that's two orbitals that are overlapping with one another to form a pi bond. And then perpendicular to that, shown in green, you have a second pi bond, right? So if you have a triple covalent bond, what that means is that one of those three bonds is a sigma bond, and then you have two pi bonds. Very, very important that we know that, because that is something that is really, really important. It heavily influences the bonding behavior and the stability and the reactivity and just everything when it comes to these compounds, right? Triple bonds tend to be shorter and stronger than double bonds, which are shorter and stronger than single bonds. That's another important fact that's good to know. So, all right, so we understand when we see a single bond, it's just a sigma bond. When we see a double bond, it's a sigma bond and a pi bond. When we see a triple bond, it's a sigma bond and two pi bonds. Very, very important stuff. All right, so let's move on. So now what we're going to do is we're going to talk about hybridization and molecular geometry. So this is another valence bond theory concept here. And I think hybridization is kind of something that confuses a lot of people and scares a lot of people away. I'm not exactly sure why. I know like it's kind of hard to interpret the images and figures and diagrams that you see because it's like a bunch of orbitals kind of like all jumbled together. So it might be hard to take all that in. But I'm going to take a crack at explaining it to the best of my knowledge, or to the best of my ability, rather. So, some basic principles when it comes to hybridization. The first principle is that bonding lowers the potential energy of the constituent atoms that are bonded together. In other words, the more bonds you can form, the more happy, the more stable your atom and the subatomic particles within that atom are going to be, right? The other thing is that atomic orbitals, oftentimes they will mix together to form something called hybrid orbitals. And the names and shapes of hybrid orbitals, they reflect the number of atomic orbitals and the type of atomic orbitals that are mixed together to form those hybrid orbitals, right? So bonding lowers potential energy. Atomic orbitals often mix to form hybrid orbitals, right? And carbon, given that carbon often forms 4 bonds, we would expect carbon to hybridize quite frequently, right? Because, again, more bonds means more stability, and the atom forms more bonds by forming these hybrid orbitals, which we're going to get into in great detail in just a moment. So the next thing that's important to remember with hybridization is that the number of atomic orbitals that are mixed together is equal to the number of hybrid orbitals obtained. Very, very important. We're going to repeat that over and over and over again. And then finally, valence electron pairs, they tend to space themselves out as far apart from one another as possible in order to achieve maximum separation, maximum distance between those electron pairs. And this is called Vesper theory, valence shell. I think I saw somebody in the chat mention it a moment ago, Vesper theory, valence shell electron pair repulsion theory, right? And that can be used to predict the geometry, the approximate bond angles within the molecule. Okay, so let's talk more specifically about hybridization. We're going to be talking about hybridization involving s and p orbitals, right? There are other hybridizations involving d orbitals, but we're going to restrict our discussion to ones involving s and p orbitals because these are the ones that are most commonly encountered in organic chemistry, right? So when you're talking about hybridization with s and p orbitals, there are 3 possibilities, right? The s orbital can combine with 1, 2, or all 3 of the p orbitals. Now, if the s orbital combines with all 3 p orbitals within the valence shell of a p block element, that's going to form 4 sp3 hybrids, right? So if you have an s orbital and 3 p's, they mix together to form 4 sp3 hybrids, right? And so if you look at this this notation here, the s sort of has an understood 1. There's 1 s orbital that went in to make those hybrid orbitals, and the p has a 3 on it, which means 3 p orbitals went in there. So for a total of 4 atomic orbitals that were mixed together to result in 4 hybrid orbitals that you get upon hybridization. So that's one possibility. The s and 3 p's makes 4 sp3 hybrids. Another possibility is that the s orbital combines with 2 of the 3p orbitals, and that forms 3 sp2 hybrids, right? So sp2, that tells us that there's 1 s orbital and 2 p orbitals in there to give a total of 3 sp2 hybrids. And finally, the third possibility is that the s orbital combines with only 1 of the 3 p orbitals, and that results in 2 sp hybrid orbitals, right? So in this notation here, there's an understood 1 on the s and the p, right? 1 s orbital, 1 sp orbital. They mix together and you get 2 sp hybrids. So let's take a look at what these atomic orbitals and hybrid orbitals actually look like. So we're going to start with sp3 hybridization here. So on the left side of your screen shows you the atomic orbitals that are mixed together, that are combined. And on the right side of your screen here, we see the hybrid orbitals that are obtained. So again, sp3 hybridization, that's when you get 1 s orbital combining with all 3 of the p orbitals, because there's only 3 p orbitals in that shell, right? The s orbital combines with all 3 of those p orbitals to result in 4 sp3 hybrids. Notice a couple of observations. One, the number of atomic orbitals that were mixed together is the same number as the number of hybrid orbitals that are obtained, right? 4 orbitals went in, 4 orbitals come out. That's important to understand. Notice also the shape of the sp3 hybrid. It's got a funky looking shape, right? It's got these 2 lobes, these 2 blobs of electron density, but one of them is significantly smaller than the other, right? These hybrid orbitals, they are asymmetrical, right? The p orbitals, those are symmetrical, but these hybrid orbitals are not symmetrical at all. And usually when you have less symmetry, that means you have less dispersal of energy, which means you have a higher potential energy. So hybridization actually costs energy. It's energetically uphill for an atom to hybridize, right? But that loss in energy, right, that high potential energy is sort of bought back, right? It's sort of recouped by the atom because in forming hybrid orbitals, those hybrid orbitals tend to overlap with the orbitals of other atoms much better to form more stable covalent bonds, right? So even though hybridization costs energy, it actually ends up helping the atom in achieving a lower potential energy in the long run by forming better overlaps with more energy dispersion within those chemical bonds, right? So these are the 4 sp3 hybrid orbitals that are formed when one s combines with all 3 p orbitals. Now, if we look at them sort of superimposed on the same atom, what does that look like? Well, it looks like this. Let me sort of move myself out of the way here for a second. So it looks sort of like this, and it gives what we call a tetrahedral geometry, right? Which means that your orbitals are pointing to the corners of a regular tetrahedron. I wish I had a tetrahedron on me. If you ever play like Dungeons and Dragons before, you know that 4-sided die, right? It's like a 4-sided figure, and all of the faces of that figure are equilateral triangles. That's what a regular tetrahedron looks like. So you can imagine how this molecule's sort of, or how this these orbitals are shaped, where they point to the corners of a regular tetrahedron, right? And so that's called a tetrahedral geometry. The approximate bond angle, and again, it kind of depends on exactly what those orbitals are doing. Are they lone pairs? Are they bonding pairs? But the approximate bond angle predicted by Vesper theory would be 109.5 degrees. And as this third point down here says, the molecular geometry, the arrangement of the atoms, is affected by the presence or absence of lone pairs. Remember, lone pairs, those are the individual non-bonding pairs that belong to individual atoms, right, within a molecule, okay? And so there's a couple of possibilities with sp3 hybridization. So we're going to discuss the 3 possibilities right here. So one possibility is that all 4 of those sp3 hybrid orbitals are involved in chemical bonding. In other words, they're all bonding pairs. None of them are lone pairs. If that's the case, then your molecular geometry, which I'm just abbreviating mg down there, see that is molecular geometry, right? If you have 4 bonding pairs, 0 lone pairs on your sp3 hybridized atom, that results in a tetrahedral molecular geometry. And the classic example of an sp3 hybridized atom with a tetrahedral molecular geometry is the carbon atom in a molecule of methane. So let me enlarge myself a little bit, right? So something like this, right? So that carbon atom, it's sp3 hybridized. It's got no lone pairs. All 4 of the electron pairs are used for bonding, and the molecule looks like this. It's tetrahedral, right? So that's one example of an sp3 hybridized atom, the carbon atom in a molecule of methane, right? Another possibility is that of those 4 hybrid orbitals, 3 of them have bonding pairs, and 1 of them has a lone pair. If that's the case, then your electron geometry is still considered tetrahedral, but your molecular geometry, the shape of your molecule, is different. It's no longer tetrahedral. It's something that we call trigonal pyramidal. And a good example of this is the nitrogen atom in a molecule of ammonia, NH3. So let me sort of blow myself up again so I can, I didn't mean to move that. Hang on. I'm going to blow myself up again just to, all right. So this is an example of a molecule of ammonia. By the way, if you would like to get your hands on a molecular model kit where you can build your own molecules like this, I do have an affiliate link in the description of this video. This is called an Old Knobby molecular model kit. Very, very fun to play with. It's affordable. And like I said, just check the link in the description if you want to get yourself one. It is an affiliate link, so I do get like a small commission, which helps to support the show. So if you're interested in getting yourself a molecular model kit, I would highly recommend it. These things are awesome. They really, really help improve your understanding of the material. So again, this is the ammonia molecule, right? So it's got 4 overall sp3 hybrid orbitals, right? But one of them has a lone pair, right? You can imagine that lone pair up here. And so the resulting shape is this sort of like pyramid that has a triangular face at the bottom, and this central nitrogen atom, you can think of that as like lifted up just a little bit, right? So that's called trigonal pyramidal. Let me move myself out of the way as we discuss the third possibility with sp3 hybridized atom. Again, I hope everybody's doing well tonight. I see a couple of messages in the chat. It's a pretty active chat. Looks like people are talking to each other, which I think is great. Kind of takes some of the attention off of me a little bit. So anyway, let's look at this other possibility, right? So we talked about 4 bonding pairs, no lone pairs. We talked about 3 bonding pairs, 1 lone pair. And then the other possibility is we have 2 bonding pairs and 2 lone pairs. I don't know why the word 1 appears here. It's just a typo. There's a lot of slides in this presentation, so this probably isn't the last mistake. So yeah, ignore that little 1 right there. 2 bonding pairs, 2 lone pairs. This is what we would call a bent molecular geometry, right? And we are all very, very familiar of an atom within a molecule who is sp hybridized and has a bent molecular geometry. And that, of course, is the oxygen atom in a water molecule. Looks kind of like this, right? So basically, when we're talking about molecular geometry, it's basically the electron geometry, but then you cover up one or more of those orbitals, right? And just imagine sort of that they're not there. I mean, they are there in the sense that lone pairs, they do apply a repulsive force, which overall governs the shape of the molecule, right? But again, with electron geometry, in all 3 of these cases, it's tetrahedral. You're looking at the arrangement of the electron orbitals around the atom. With molecular geometry, you're just looking at the arrangement of the atoms. And so for the water molecule, we call that a bent molecular geometry. All right, so that is sp3 hybridization. We're going to move right along and talk about sp2 hybridization. So sp2 hybridization, that's when the s orbital in the valence shell combines with 2 of the 3 p orbitals to result in 3 sp2 hybrid orbitals. So notice, just like we saw with the sp3 hybridization, is that the number of atomic orbitals that are mixed together is equal to the number of hybrid orbitals that are obtained. In this case, that number is 3. The s and 2 of those p orbitals combine to form 3 sp2 hybrid orbitals, and they look sort of like this, right? So again, if we look at this, an sp2 hybridized atom with those hybrid orbitals sort of superimposed on the same atom, what does that look like? Well, it looks like this. So, whoops, let me give a little bit more room here. There we go. Actually, I'll just kind of move myself down here. That's probably the best spot. All right, so this is sort of what the orbitals look like on an sp2 hybridized atom, right? So this gives something called a trigonal planar geometry, which means that your hybrid orbitals point to the corners of an equilateral triangle. And to get a good visualization of this, it's I've included sort of a top view. So if you were looking at this image from the top, it would sort of look like this. So those 3 hybrid orbitals are pointing to the corners of an equilateral triangle. We call that trigonal planar geometry. The approximate bond angle associated with sp2 hybridization is 120 degrees. And notice also that, if we think about this, right? So there's an s orbital, there's 3 p orbitals, the s orbital combined with 2 of the p orbitals to make those 3 sp2 hybrids. But what about the 3rd p orbital that wasn't involved in hybridization? What happens to it? Well, nothing. It's left alone. It is unhybridized, right? So this purple thing right here, both of these lobes together, this whole purple thing right here that I'm sort of hovering over with my mouse cursor, that represents a single unhybridized p orbital, right? So when you combine the s with 2 p's, you get 3 sp2s, but you also have an unhybridized p orbital that's kind of just hanging out along for the ride. Very, very important that we understand that. All right. And also, of course, the molecular geometry of an sp2 hybridized atom is affected by the presence of lone pairs. Let me grab a drink of water. All right. So let's look at the possibilities along with a couple of examples here. So let me make sure I'm not in the way of any text. Doesn't look like I am. All right. Okay, so one possibility with sp2 hybridization is all 3 of the electron pairs, all 3 of the orbitals are bonding pairs, and you have 0 lone pairs. That would result in something called a trigonal planar molecular geometry. Okay, so one example of this would be the carbon atom in a molecule of CH2O. So that CH2O formula. That is called formaldehyde. You might be familiar with it. And it looks sort of like this, right? You've got your carbon in the middle, bonded to an oxygen. It's also bonded to two hydrogen atoms, right? And so you can see that the angle between two bonds is roughly 120 degrees. It's probably going to differ from the exact 120 degree angle that's predicted by Vesper theory, because the bond to the oxygen atom is not really equivalent to the bond between the carbon and the hydrogen atoms, and so they're probably going to have different repulsive power between them, right? So, but the approximate geometry is trigonal planar, and the bond angle between these is close to the 120 degree bond angle predicted by Vesper theory, right? So that's when you have sp2 hybridization, 3 bonding pairs, no lone pairs. What if you had 2 bonding pairs and 1 lone pair? What would that look like? Well, that would look like this over here, right? That would result in something called a bent molecular geometry. So we saw a bent molecular geometry a moment ago with water. This is a different bent molecular geometry because unlike the water, which had a bond angle of roughly 109 degrees, this bent molecular geometry has a bond angle of roughly 120 degrees. And the top view, or the view from the top of this model, is sort of shown here. So you can see where that 120 degree angle sort of comes in. And a good example of this sort of geometry would be the sulfur atom in a molecule of sulfur dioxide. So this is a molecular model for sulfur dioxide, right? The sulfur bonded to 2 atoms, right? It's sp2 hybridized, but notice it's got that bent sort of geometry, roughly 120 degree angle between those two. All right, so that was sp2 hybridization. We are going to move right along, and we are going to talk about sp hybridization. So sp hybridization, that's when one s orbital combines with one of the 3 p orbitals to form 2 sp hybrids. Notice, just like the last 2 examples, the total number of atomic orbitals that are mixed together is equal to the total number of hybrid orbitals that are obtained upon hybridization. We have 2 orbitals, 1s, 1p, and they hybridize to form 2 orbitals, 2 sp hybrids, right? And so what does an sp hybridized atom look like? What do those orbitals look like when they're all superimposed on top of one another? Well, looks kind of like this. I couldn't find really a good image online of something like this, so I kind of drew one myself. So let me kind of explain what's going on here, right? So this yellow blob over here represents one sp hybrid orbital. This yellow blob over here represents another sp hybrid orbital. And then this entire thing that I'm hovering over with my mouse cursor represents an unhybridized p orbital. And this thing over here, that's sort of cutting through the plane that's formed by the other orbitals, this thing right here, that represents another unhybridized p orbitals. Because remember, there are 3 p orbitals total. So if the s only combines with one of those 3 p orbitals, then the remaining 2 p orbitals are going to be left alone. They're going to be unhybridized. Okay? And the geometry predicted by Vesper theory associated with an sp hybridized central atom is roughly 180 degrees, and we call this a linear geometry, right? And a good example of this would be the carbon atom in a molecule of hydrogen cyanide, HCN. So hydrogen cyanide is some pretty nasty stuff. I think it was actually used in like gas chambers in the Holocaust and World War II. It's pretty bad. But anyway, so this carbon atom, right, it's got these 2 sort of hybrid orbitals, right? These 2 sp hybrids that are governing the shape of this molecule. And notice that it's linear, right? If I sort of turn the molecule like this so that you're looking down the bond, you don't really see much behind it. It's all eclipsed, right? All 3 of these atoms, the carbon, the nitrogen, and the hydrogen, are collinear. They can all be drawn. The nuclei of these atoms can be drawn in the same line, right? So that's sp hybridization. So we talked about sp3, sp2, and sp hybridization. So hopefully it's coming back to us. Hopefully we're sort of, bringing ourselves back up to speed with this general chemistry stuff, because boy, I tell you, it is going to come back with organic chemistry. All right. So now is the part where we're going to talk about how to predict hybridization and geometry around a central atom within a molecule. Okay, so it's a step-by-step process. If you follow all the steps carefully, you should get to the correct hybridization and geometry with the correct approximate bond angle every single time. The first thing that you want to do is to identify a central atom. Again, central atom just means it's bonded to two or more other atoms. And of course, this requires the correct Lewis-Kekulé structure of the molecule, which we reviewed how to do some time ago. And there may be more than one central atom for larger molecules. This happens a lot. So central atom doesn't mean like one individual atom within the whole molecule. Central atom just means it's bonded to two atoms or more. So it's entirely possible to have more than one central atom in a molecule. Just depends on the size of the molecule and all that stuff. So identify the central atom. Step number 1. Step number 2 is to count the number of sigma bonds and lone pairs around the central atom, right? So you look around that central atom and you ask yourself, how many sigma bonds and lone pairs are around that central atom? Once you figure out that number, you move on to step 3, which is to select the hybridization based on the number of orbitals that are required to hold electron pairs from step 2 above, right? So in other words, if I find that there are 4 sigma bonds and lone pairs around a central atom, well, it's going to require 4 orbitals to accommodate all those electrons. And so which hybridization is associated with 4 orbitals? That would be sp3, right? The s combines with 3 p's to make 4 sp3 hybrids, right? So you select hybridization based on the number of orbitals that is necessary to hold the electrons from step 2, where you count the number of sigma bonds and lone pairs around your central atom. Step 4 is to understand that the approximate bond angles predicted by Vesper theory are related to hybridization. So if you have sp3 hybridization, the approximate angle is 109.5 degrees. If you have sp2 hybridization, the approximate bond angle is 120. And finally, if you have sp hybridization, that's a approximately 180 degree bond angle around that central atom. And finally, number 5 says to visualize the molecular shape using Vesper theory, taking into account which electron pairs are bonding pairs and which electron pairs are lone pairs. Kind of like what we were talking about earlier between methane and ammonia, right? The carbon in methane and the nitrogen in ammonia are both sp3 hybridized, but they have different geometries because of the number of lone pairs and bonding pairs around the central atom. So if it's all right with you guys, I would like to take the opportunity to practice on a couple of molecules where we look at a chemical formula and predict the hybridization and the geometry around a central atom. So let's do that. So in order to do that, what we're going to do is we are going to hop right over to the whiteboard. I got a couple of examples just off the top of my head that I want to sort of do. And yeah, so here we go. So how about we start with C2H4, right? So C2H4, that's my chemical formula. What I want to do is to be able to determine the hybridization and the geometry of all of the central atoms within this molecule, right? So the first thing we want to do is to draw the Lewis-Kekulé structure for this molecule, right? So the first step when we're doing that is to count the total number of valence electrons. Carbon, right, that has 4 valence electrons because it's in group 4 of the periodic table. And there are 2 carbons, so we have 4 times 2, or 8 valence electrons coming from that carbon atom. For hydrogen, hydrogen has 1 valence electron because it's in group 1, and there are 4 hydrogens, so 1 times 4, for a total of 4 hydrogens in this, 4 hydrogens, but 4 valence electrons coming from hydrogen in this structure. There aren't any pluses or minuses, so I'm not really going to worry about adding or removing electrons. We don't have to take care of that step. So we have a total of 12 valence electrons, right? So at the end, when we're done drawing our Lewis structure, Kekulé structure, whatever, we need to make sure that it has a total of 12 valence electrons in it. The next step is to draw the correct arrangement of the atoms, right? And the only arrangement of the atoms that makes sense at all is to have the carbon atoms connected to one another, and then each carbon atom has 2 hydrogens connected to it. This is the only possible arrangement. Why? Because hydrogen can only form one bond, so hydrogen cannot be a central atom. Hydrogen cannot form 2 bonds, right? So this is the only arrangement that works. Carbons connected together, each carbon has 2 hydrogens connected to it, okay? So that's the arrangement of the atoms. The next step is to place a single covalent bond, which remember has 2 electrons, single covalent bond between every pair of neighboring atoms, right? So I'm going to put a single covalent bond here, one there, one there, one there, and one there. So how many electrons do we use up by giving those single covalent bonds? Looks like 2, 4, 6, 8, 10. So we used up 10 valence electrons, so we're going to remove them from our valence electron count. That leaves us with 2 electrons. So the next thing we want to do is we want to place lone pairs on atoms, giving as many atoms an octet as we possibly can, right? Obviously, we're not going to put any lone pairs on hydrogen because hydrogen only has that single 1s orbital in the n equals 1 principal shell, so hydrogen doesn't have any room. It can't get any lone pairs. It's not even possible for hydrogen. The only place that we can put a lone pair is on one of these carbons. So I'll go ahead and stick it right there. Now what we have to do is we have to check to see if the carbon atoms have an octet. This one does. This one over here on the right does not. How do we solve that problem? Well, we solve that problem by taking a lone pair and moving it into the bonding region between the 2 carbon atoms to form a double covalent bond, right? A double covalent bond. And now that is how we get the correct Lewis dot structure for this molecule, right? And you can pause the video or stream if you want and confirm for yourself that all non-hydrogen atoms have an octet and all hydrogen atoms have a duet, right? And just because I am me and I prefer Kekulé structures over Lewis structures, I'm going to erase these dots here and replace them with lines, right? So we got a double bond between those carbons, and we got single bonds between the carbon and the hydrogen. Okay, so we have a correct Kekulé structure for this molecule, so we are definitely getting somewhere, right? And notice that these atoms are equivalent. These 2 carbon atoms are equivalent, right? So whatever applies to one of these carbons, right? They're both considered central atoms, right? But whatever we say about one of these carbons also applies to the other carbon because they're indistinguishable from one another. They have the same sort of situation, right? They have a double bond and they have 2 single bonds, each to a hydrogen atom, right? So if we know the hybridization and geometry around one central atom, we're going to know the hybridization and geometry around the other central atom, right? Okay, so the next thing now that we have identified our central atom is to count the number of sigma bonds and lone pairs around the central atom. So if we look at this carbon here, how many sigma bonds and lone pairs are around this central atom? Well, it looks to me like we have one here. Actually, that's not a good notation because that implies that we have a double bond there. So we have one here, we have one here, and we have one here. So it looks to me like we have a total of 3 sigma bonds / lone pairs, right? We don't have any lone pairs, but we have 3 sigma bonds. So, and again, you add them together, right? So we have 3 sigma bonds and lone pairs. Notice that I didn't count this double bond as 2 sigma bonds because we understand now, especially, that a double bond is not 2 sigma bonds. A double bond is a sigma bond and a pi bond, right? So we know we have 3 sigma bonds and lone pairs around this carbon atom. Then what we're going to do is we're going to select hybridization based on the number of electrons that is required to hold 3 electron pairs, basically, right? So 3 electron pairs, how many orbitals does it take to hold 3 electron pairs? That would be 3. And what is the hybridization that is associated with 3 orbitals? How many atomic orbitals do you have to mix together to form the hybridization that includes 3 orbitals? That would be sp2 hybridization. Remember, because sp2 is the hybridization in which one s orbital combines with two of those 3p orbitals to make 3 sp2 hybrids, right? So we know that the hybridization around that carbon is sp2, and again, the approximate bond angle is related to hybridization. The bond angle associated with sp2 hybridization is 120 degrees, or approximately 120 degrees. It's probably a little different than that because, one of these is a double bond around it, the other 2 are single bonds, but that would be sort of how you do that, right? So, all right, let's move on to the next example in which we figure out the hybridization and molecular geometry around a central atom. So let's do another fairly simple molecule. How about we do, let's say we have C2H6. So we did C2H4 earlier, now we're going to do C2H6. What is the hybridization and geometry around the central atoms within this molecule? Good question. Let's figure it out. So the first thing we need to do is to write or draw the Lewis-Kekulé structure, right? So the first step with that is to count the total number of valence electrons. We have carbon, we have hydrogen, right? There are 2 carbons that have 4 valence electrons, so 4 valence electrons times 2 carbons. So that's 8 coming from the carbon. And then for hydrogen, we have 1 valence electron, and we have 6 hydrogen atoms, each with 1 valence electron. That gives us 6 valence electrons coming from the hydrogen. 8 plus 6, that's 14 valence electrons, right? So the next step is to draw the correct arrangement of the atoms. The only possible arrangement of atoms for a molecule with this chemical formula is to have the carbons connected to one another. I just realized I guess I can pull this down here to make a little bit more room. Yeah. So the only correct arrangement that is even possible is to have the carbons connected to one another, and each carbon has 3 hydrogen atoms connected to it, right? Because again, hydrogen only forms 1 bond. It cannot be a central atom. The next step is to take our valence electrons and start placing them in this structure, giving a single covalent bond between every pair of neighboring atoms. So there's 2, 4, 6, 8, 10, 12, and look at that. We used all 14 of our valence electrons. We have 0 remaining. They're all sort of accounted for, right? And then if we had more valence electrons left, we would start putting on lone pairs, but we can skip that step because we don't have any valence electrons left in this Lewis structure. And then also, if one of these atoms didn't have an octet, we would maybe move lone pairs in to make double bonds or whatever. But as you can see, we don't need to do that step either, because if you look at both of those carbons, each carbon has an octet, each carbon has 8 electrons around it, and of course, each hydrogen has a duet, so all of these atoms are valence satisfied. They're happy, right? And again, because of my own personal preference, I am going to replace these dots with lines. I'm going to convert my Lewis structure to a Kekulé structure. So this is what our Kekulé structure of this C2H6 molecule would look like, right? Okay, so now that we've done that, let me sort of erase this stuff in blue over here that we no longer need. So now what we're going to do is we're going to identify our central atom. Of course, we could pick either of these carbons because the symmetry of this molecule, each of these carbons they're equivalent to one another, right? So whatever we say about one carbon, we're saying about the other, right? So if I focus on this carbon here, we are going to identify that as our central atom. Then we are going to count the number of sigma bonds and lone pairs around this central atom. Looks like we have, I'll go ahead and just star them here. We have 1, there's a sigma bond there. 2, there's a sigma bond there. 3, another sigma bond. And 4, and I don't see any lone pairs, so it looks like we have 4 sigma bonds / lone pairs, right? 4 sigma bonds / lone pairs. So how many orbitals is it going to take to accommodate all those electrons? Well, it's going to take 4 orbitals, right? And which hybridization gives us 4 orbitals? That would be sp3 hybridization, right? Because sp3 hybridization is when one s orbital combines with 3 p orbitals for a total of 4 sp3 hybrids, right? And again, the approximate bond angle is related to hybridization predicted by Vesper theory, which for this would be approximately 109.5 degrees, right? So that is the hybridization and geometry of this molecule here. So pretty straightforward. Again, this might seem like a lot, but again, I'm assuming that you guys have already been exposed to this stuff before. And so, I'm sort of going through it very, very deliberately and explicitly, talking about all the steps that I'm doing and that I'm not doing along the way. But if you're doing this individually and you're practicing, you can bang these out much more quickly than I'm doing over this live stream right now. So, all right, let's do just a couple more, and then we'll be wrapped up. Looks like we're already over an hour on this stream. Everybody who's watching, how y'all doing? Everybody still with me? I hope so. I hope I'm not just talking into a microphone for no reason. So, all right, so let's do another one. How about we do C2H2? C2H2. That's our chemical formula. We want to know the hybridization and geometry of the central atoms, right? We'll start with the Lewis Kekulé structure, right? So we've got 2 elements. We've got carbon. We've got hydrogen. Carbon has 4 valence electrons, and there are 2 carbons. So that gives us 8 valence electrons on account of carbon. Hydrogen has 1 valence electron, and there are 2 hydrogens, giving us 2 valence electrons coming from hydrogen. That gives us a total of 10 valence electrons to play with in this Lewis dot structure. Next thing we're going to do is draw the correct arrangement of the atoms. There's only one possible arrangement, which is carbon atoms connected to one another, and each of these carbons is connected to a hydrogen also. Got a message in the chat from Valerie Medina. Says, thank you. This will help my next tests. Awesome. I'm very, very happy to hear you say that. Very cool. Or I'm happy to read you saying that. You know what I mean. All right. So we've got the correct arrangement of the atoms here. So we're moving right along. The next step is to place a single covalent bond between every pair of neighboring atoms. So there's a single covalent bond between these 2, single covalent bond between these 2, and a single covalent bond between these 2. How many electrons did that account for? It looks like that accounted for 2, 4, 6 valence electrons. So if we start out with 10 and we take away 6, that's going to leave us with 4 valence electrons left. What we're going to do with those 4 valence electrons is we're going to assign them as, go back to black here, we're going to assign them as lone pairs on the individual atoms. So I put a lone pair on that carbon and a lone pair on that carbon. All right, so that takes care of that. So we have 0 valence electrons remaining. Then what we're going to do is we're going to check to see if all of the atoms are valence satisfied. In other words, do the carbon atoms have an octet? And they don't. They don't, right? If you look at each of these carbons, they have 6 electrons around them, not 8. That's a problem. We solve that problem by taking the lone pairs, moving them into the bonding region between the atoms. In this case, we're going to move both lone pairs from the carbons into the bonding region between them. So I'm going to take that lone pair, and I'm going to stick it there. And I'm also going to take this lone pair, and I'm going to stick it there also. So we have just successfully formed a triple covalent bond, right? And if you look at the carbon atom, right, does it have an octet? Yes, it does. You've got 2 electrons over here. You got 6 over here. So the carbon atom is happy. It is stable. All right. So I'm going to convert this to the Kekulé structure real quick because it's just more aesthetically pleasing to me. So we have a carbon triply bonded to a carbon, singly bonded to hydrogen atoms on each carbon, right? And this chemical has a name. This molecule has a name. It's called acetylene, or ethine if you're naming it systematically. We'll talk more about systematic IUPAC nomenclature later on. All right, so we have a correct Kekulé structure for this molecule. Of course, the next thing we want to do is to identify a central atom. Of course, it's going to be the carbon. Each of these carbons are equivalent to one another, so whatever we say about this carbon is true of the other carbon as well. So for the purposes of hybridization, what do we need to do? We need to count the number of sigma bonds and lone pairs around the central atom, right? How many sigma bonds and lone pairs are around this carbon? Looks like we have one sigma bond there. We have one sigma bond here in this triple bond. Remember, because a triple bond is composed of a sigma bond and two pi bonds. So we're just counting the one sigma bond. We have no lone pairs. So in total, that means we have two sigma bonds and lone pairs, right? Two sigma bonds and lone pairs. How many orbitals does it take to accommodate the electrons in two sigma bonds / lone pairs? Well, it takes two orbitals, right? And which hybridization is associated with two orbitals? That would be sp hybridization. Sp hybridization is what happens when the s orbital combines with one of the three p orbitals to result in two sp hybrids. And what is the approximate bond angle associated with sp hybridization? That would be approximately 180 degrees. This would be a linear geometry, right? So instead of trying to, memorize, the angles and the hybridizations and all that stuff, try to resist memorizing and just think about it from a bottom up, principle point of view, and you'll be able to sort of figure these out by reasoning your way through it. Okay. So let's do, I guess, one more. Let's do one more, just for the sake of it. We've done carbon over and over and again, so let's do one that doesn't have carbon in it. Let's try NH4+. NH4+. What is the hybridization and geometry of the central atom in this molecule? Okay, so we're going to start with the Lewis structure, of course. We have two elements. We have nitrogen and we have hydrogen, right? Nitrogen has 5 valence electrons and there's only one nitrogen. Hydrogen has 1 valence electron and there are 4 hydrogen atoms. So we have 5 plus 4, that's 9 valence electrons. Also, we have this positive charge here, right? And the rule with ions is that we take an electron away for each plus that we see, and we remove, and we add an electron for each minus that we see. So we're going to take an electron away on account of this positive charge, right? So because of that positive charge, we're going to remove 1 electron. So we have 9 minus 1. So that's a total of 8 valence electrons. 8 valence electrons. The next step is to draw the correct arrangement of the atoms. In this case, the only arrangement that makes any kind of sense whatsoever is to have the nitrogen atom bonded to 4 hydrogen atoms, right? Because the hydrogen can't be a central atom, right? The next thing that we're going to do is we are going to place a single covalent bond, which of course is 2 electrons around every pair of neighboring atoms. So there's a single bond, there's a single bond, there's a single bond, and there is a single bond. So that looks like it has accounted for all 8 of our valence electrons. We have no more valence electrons remaining. And again, because I am a nitpicky snob, I'm going to convert this Lewis structure to a Kekulé structure, replacing those pairs of dots with lines. Just looks better to me. All right, so that's our Kekulé structure for NH4+. And usually we'll give a positive charge to this nitrogen here. I haven't really gone into like formal charge and stuff like that yet, but we're going to save that for the next stream, I think. All right, so we have our Kekulé structure, so we can erase all that stuff. So then the question becomes, where's our central atom? Of course, the only possibility is this nitrogen atom. That's our central atom that we've identified. Then the next question is, how many sigma bonds and lone pairs are around that nitrogen? Looks like we have 1, 2, 3, 4 sigma bonds, right? 0 lone pairs, giving us a total of 4 sigma bonds and lone pairs, right? If you have 4 sigma bonds / lone pairs, then that means it's going to take 4 orbitals to accommodate all of those electrons. The hybridization that is associated with 4 orbitals is... Can anybody name it? I know there's not a lot of people in here right now, but the hybridization that is associated with 4 orbitals, right? What is it? Yes, person I just imagined who didn't actually type in the chat. It's sp3. sp3 hybridization. Remember, that's when one s orbital combines with 3p orbitals to produce 4 sp3 hybrid orbitals, right? And also, we understand that the approximate bond angle associated with 4 sp3 hybrid orbitals, right? 4 electron pairs spacing themselves out as far apart from one another as possible to achieve maximum separation. That approximate angle is 109.5 degrees, right? So it all starts with drawing the Lewis Kekulé structure. Then you identify your central atom. You count the number of sigma bonds and lone pairs. You understand the number of orbitals that is required to accommodate all of those electrons, and then you connect the number of orbitals to the hybridization. 4 orbitals, sp3 hybridization. 3 orbitals, sp2 hybridization. 2 orbitals would just be sp hybridization. And then your approximate bond angles are related to hybridization. So I hope that was helpful. I want to take you guys back to the PowerPoint. We have one more slide that I want to look at, which is what we're going to be talking about on the next episode of the Organic Chemistry. So originally, I really wanted to do one stream in which we covered all of the general chemistry content that was needed for organic chemistry, but I unfortunately didn't have enough time to prepare one big stream that had all of it in there. So we're going to save these topics that are shown here in blue for the next episode. So those topics are electronegativity and bond polarity. We're also going to be talking about formal charge, very, very important. We're going to be talking about resonance, hugely important and very commonly misunderstood. So I'm going to spend some time going over resonance. And we're also going to talk a little bit about acid-base reactions and acid-base behavior of organic molecules that we'll see over and over again as we continue our exploration into organic chemistry. So sorry about that audio. Thank you everybody for watching. I truly, sincerely hope that the stream has been valuable to you. Again, if you'd like to support the stream, your support would be very, very welcome, whether that means leaving a thumbs up, donating to the stream via PayPal. I think I have crypto links in the description too. You can donate via crypto. I don't know if I have them in there or not. Or you can get yourself an old knobby molecular model kit using the affiliate code, or the affiliate link rather, that is in the description. Thank you guys for those of you who are considering supporting. I really appreciate it. Really, really excited about this stream. I think it was a great stream. I hope you guys would agree. And then, of course, going to be also excited about next week, where we finish up all the general chemistry stuff. And then the following week, we'll get straight into the nitty-gritty of organic chemistry, alkanes, cycloalkanes, structure, nomenclature, reactivity, everything. I am really, really looking forward to it, and I hope you are as well. So I will see you in the next episode of the Organic Chemistry. Have a good night.